Hello developers, let's start developing. So today we're taking on the 8th day of the 2024 Advent of Code. I've read through the task and basically we have some antennas that the Easter Bunny put up. He is the traditional enemy of Santa Claus according to the Advent of Code lore. So we have those things and we need to detect where a thing called antinode is. This antinode is, so if we have antennas, we have different frequency antennas and they are denoted by a different symbol. So all the zeros in this thing are the same and all the A's are the same, but the zero and the A's are different. And two antennas of the same type will create two antinodes. Basically, if we draw a line through the antennas, there will be one that is equidistant from the first one and one from the second one. So basically the distance between the hash and this A is equal to the distance between this A and this A, and same goes for this. So basically they are on the other side. It's like this antenna gets replicated here and this antenna gets replicated here in respect to this one. That means that if we have three antennas, we will have three pairs of antennas. That means that we will have 6 items. And if we have 10 antennas of the same time, that will be 45 different pairs, which means that we're gonna have 90, possibly 90 antinodes. The antinodes cannot be out of bounds, so we're only counting the ones that are in bounds. But note that an antinode can be on top of an antenna, and that's legal. But what can also happen is that we can have an antinode that's on top of another antinode. And those need to be counted once, because the question is, this is a landmine that I guess a lot of people will fall into. How many unique locations within the bounds of the map contain an antinode? So if a location contains 5 antinodes, it means that it contains an antinode. So it means that we're gonna have to count the unique locations. Anyway, let's get started. We have the small input here. Let's try to parse it. We have the lines, so we're not gonna do anything too fancy. We're just gonna say lines.map. Each line, we're just gonna split it on every character, which will actually result, instead of having a string array, we're gonna have a string matrix. So we're just gonna return the matrix. Let's check if this thing actually works. I will use a helper method that I have that's called print matrix, print the input matrix. If everything runs well, we should get an echo of the input. And seems like we get that. Cool. Now, let's start with this. First of all, I'm gonna need to know where all the antennas are. So I will just loop through everything. First, let's get the width and the height. We have the width and the height of our matrix, and now we can say for loop, and this will be the row index, and the row index goes from 0 to less than the height. And we're gonna have another nested for loop. Let's see if it guesses. Well, it guessed something. I have no idea if this is correct, but this part is correct. So if the cell is a dot, we can continue because that's not an antenna. Otherwise, we have an antenna. which means that I will actually create antennas as an object, not as an array, because I would like to have a lookup here. So if antennas of cell is undefined, and I will need to type this. This will be a record basically, where the key is a string and the value will be a point array. And what is a point? Let's type that. Yeah, it's exactly this. It's something that has an X and a Y. So if antennas doesn't have a cell, then we're gonna set it. The count is 1. No, we're not doing that. A cell is a new array where we have the X and the Y. Otherwise, yeah, we're gonna do this. And since I really don't like else's, I can just do this. I don't like else statements in principle because they're kind of hard to read. So if we don't have, if it's the first time we're encountering a particular type of antenna, we're just creating an empty array. Over that, we're creating an property as well. And when we finish this, we should have, in this case, an object that has two properties, 0 and A capital A, and has those two 4, and this is the property 0 is an array of 4 points, an array of A is 3 points. I think I'm making sense, a bit of sense. So, and that is exactly what we get. So X, the 8th thing in row number 1, and then something in row number 2, and row number 3, and row number 4. Yeah, that's it. Seems about right. Yeah, those are the two A's. Let me just check something. If I have a lowercase a, whether that will be a separate property. Yes, it is. You see, lowercase a, uppercase a, those are different types of antennas. Let's just revert it to the proper demo input. So now we have the antennas. And now we will just need to loop through them. So I will use something that I rarely use. It's gonna for in loop that is looping through the antennas. So we don't really need this. The key is the name of the antenna, the frequency of the antenna, and the element is the array. Let's just call it array of antennas. That key has that many antennas. Let's check this. You can never be too careful. It should say 0 has 4 points, A has 3 points. And now we're gonna do a pairwise analysis. So what I'm thinking of doing, we're gonna need a bit of math, I guess. So if we have one, let's imagine that we have a one-dimensional case. So we have one antenna at 7 and one at 10. So in order to get from 7 to 10, we need to take this one and then from add to that the distance between them, and the distance between them is this much. Yeah, let's just fix that. So if we want to move from 7 to 10, this is how we go. But if we want to go the same distance but in the opposite direction, then we will just need to do a minus sign here. And if I'm correct, this should give me 4, which is the location of that antenna. And this means that this is actually, this is minus, this is plus, which means it's 2 times this minus this. So we get that, and consequently it means that since we randomly changed it, that this should give me the other one. Yes, so from 7 and 10 we are getting 4 and 13, which are the positions of the antinodes. So the math is that for a pair we can determine the places of the antinodes. So we're gonna have to have yet another set of nested loops. But this can be a 4 off. No, this can be a 4. So with this is gonna be findex, the first element, and then we have the first point. And we're gonna need to have the second element and the second point. This doesn't make any sense, but this thing is what we need. So we're starting from findex plus 1, so the next thing. So we're going first and second, first and third, first and fourth, second and third, second and fourth. We're not redoing second with first again. So we have them, and so we're gonna have to determine the position of the two antinodes. So the first antinode will be anti1. No, the x will be 2 times first dot x minus second of x. Yes, 2 times the first one minus the second one. And note that this will be mirrored for the y. And on the second one, we're doing the second, 2 times the second minus the first one. And we're gonna need to, actually I can try something like this. I can just say if, yeah, we need this, not continue, but so this means that this antinode is out of bounds. So I will actually need to invert this. Do I have such a refactoring handy? No, not really. So I will need to do it by hand. This is error prone. Let's try to convince Copilot to write it. No. Yeah, that one. So it needs to be more or equal to 0. 0 is quite okay, and we're gonna need to add this one. Know that if you make an error, Copilot will kind of propagate your error on. So we're just gonna set input of anti1, if input of anti1 to a hash. So let's have that. And of course we're gonna need to do the same thing for anti2. Its Copilot is really great for this kind of scenarios. And after we're done with everything, we're just gonna print matrix input. Let's see what we get now. If we're correct, we should get something that should look like the solution. So this, in the first row we have two hashes. One is all the way at the end, second row one hash, third row those two hashes, that hash, that hash, that hash, and the last ones are over there. Perfect. This looks great. So it means that we are kind of generating the hashes correctly, but we don't need to do this. Our goal is not to actually set them. We will have yet another thing that where we will say this is the list of anti-node locations. And this is a no, this is a set of strings. And I will also add a toString, point toString method. Yeah, we can even be fancy and add parentheses because it's easier to compare strings than to compare sets of numbers. So I will just say this added to the list of anti-node locations. And same here. What happens if we already have an anti-node in that location? Who cares? It's not gonna. This is a set. A set can only have an element or not have an element. It cannot have an element twice. It just has it. So now instead of that, I can just say console log. Yeah, just log the set to see what we have. And this is the set of locations that we actually have. Let's see how many we have of them, because that's what we need. So we're gonna need to say anti-node locations dot size. It's not length, it's size for sets, and this should be 14. Yes, it is 14. Let's take our huge input and see how this thing goes. It says we have 278 different anti-node locations. Let's check if that is the correct code. And it is. That's great. We have one more gold star. Let's see what the second part is. First time that I'm seeing this. Resonant harmonics. Yay! At any grid position exactly in line with at least two antennas of the same frequency, regardless of distance. Position of each antennas. With at least two antennas. Any grid position exactly in line with at least two antennas of the same frequency regardless of distance. So these two we have something in radio electronics called resonant harmonics, and it seems that we need to do that. So if we have a line at any grid position exactly in line with at least two antennas of the same frequency regardless of distance, which means that if we have two antennas, each time that we get something that is on the same line, we will have an antinode, which means that these two A's will generate antinodes along that line all the way. Great. And if we have two antennas, 1A here and 1A here, that whole row will be A's. And an additional thing, the three T-frequency antennas are all exactly in the line with two antennas. So they're also antinodes. So this means that if we have a pair, the points of the pairs also count as antinodes. So we're gonna need to use the same code, only a bit different. So I will just copy and paste this. Of course, we could extract this to a method, but for the sake of clarity, let's just copy and paste this. So we have our code that detects the antennas, that's still the same. We will still have a set to determine the antinode locations. Only now, for each pair, we're gonna need to do something different. What? To be honest, I have no idea. We're gonna need something like this. That I'm sure of. So now, if we have a pair, by definition, we will need to find all the antinodes on that line. What is the line? How do we get that line? We're gonna need some more math. And this time we're gonna need to use it two-dimensional, because we're gonna need to, I know, I have an idea. We're gonna need to find the distance. So let's say we have a point 2, 3 and another point 3, 5. So the distance between these points is 1 and 2, which means that, and we're gonna need to get the LCD of this, the lowest common, to somehow make this even. We'll need to find all the points on this line, because let's see what happens now. We have these things, and these are 2 apart and 2 apart. But, so my first instinct was, so we're gonna take this and apply it to this one in both directions. So we're gonna get, before this is, we're going 1 down, so that's, let's have this as 3. That's 1, we're going 2 down, that's 1. Once more, we're going 1 down, that's 0. We're going 2 down, that's -1. That's red. We overshoot. Let's move this out of the way. So in the original example, I think we have 10 items. So we're continuing in the other direction. We're just going 1 and 2, 4 and 7, 1 and 2, 5 and 9, 1 and 2, 6 and 11, and this overshoots. So all of these 5 points are antinodes. This is great. But what happens if we have this scenario? We have 2, 2. We're gonna go 0, 1. We're gonna go -2, -1. And this overshoots. And we're gonna go 6 and 8 and 10. And we're gonna go 7 and 9 and 11, and this also overshoots, and you could say that we're done. But note something else. What happens with the 3, 4 point? The 3, 4 point is on this line as well. It's exactly between those two. We have a situation like we have a C here, for example, to a C here, which means that this point is right in the middle of them. So it should be also a antinode. Well, great. What we should do, once we determine that it's 2, 2, and these two are not mutually prime, we will need to reduce them to 1, 1. And here I will try to use copilot, which means that I will need a method like this. So make coprime, which takes two numbers and does that. Let's try it this way. Yes, this is what I need. Because it actually, I want to reduce that point to something else. So if B is 0, return A. If A is 0, return B. I would want to test this a bit. It generates totally sucky test cases, but I want to see what would happen 3, 3. It should be 1. And another situation is one that I kind of already mentioned. If we have one thing that's on 1, 1 and another that is on 1, 7. So those are two in the same x and the different y. So all the points in between. So now the difference is 0, 6. 0 something should be reduced to 0, 1. And of course 6, 0 should be reduced to 1, 0. This is kind of a special case. I'm not sure if this makes sense for, in general, for whether two numbers are coprimes, but it is something that we actually want. And I will just console log this. I have a test method just for such an occasion. And we need an extra parenthesis everywhere, and we just need to run the tests. npm what? Test. And we got an error in the code that this thing generated because GCD, and yes, somebody is wrong here. I am kind of concerned that this is correct. So let's add this here. It should run now. Yeah. So let's see what happened. 2 and 4 got down to 1 and 2. 3 and 3 got down to 1 and 1. That's correct. 0, 6 is 0, 1. 6, 0 is 1, 0. Okay. What happens if one of them is negative? One minus two. Yeah, let's actually try this as well. minus 6, minus 6, 0, and also this, minus 2, minus 4. Note that in this case, we would be totally okay with whether we get minus 1, minus 2, or 1, 2. It's okay. We got the very rare, extremely rare negative 0. It's an actual thing, but it's not different from the regular 0, so we have minus 0, 1, 1 minus 0, and that is totally fine with that. Seems that this thing works. Let's leave it at that. So now, we're gonna need to find the difference. The delta is a point which is this. So now we're gonna actually need to make it coprime. And we have the delta. And now it doesn't really matter what we do. So we're gonna start from the first one or the second one. It doesn't really matter because we actually, in the delta, we have the direction. So we have this and we have a certain direction that passes through everything. So we're gonna need to move left and right, kinda, in the positive and the negative direction until we run out of bounds. We don't care whether it's actually positive or actually negative, but what we will do is basically run through 2 for loops, basically. So we can say let index or multiplier equals 0 actually. So we're gonna let our multiplier be 0 because we want to go through all of the positive and negative numbers. So basically, if we look at this thing in regards to this thing, for example, this means that on this line we will have a certain delta, and then what we can do is take a multiplier, and if that is 0, we will get the selected A. If that is minus 1, we will get a point over here. If that is minus 2, we will get a point over here. If that is plus 1, we will get a point over here and over here. So one way to do it, we can have a loop that goes from, I don't know, minus 1000 to plus 1000 or something weird like that. But I will make 2 loops, one that goes from 0 to until we run out of bounds, and one that goes from minus 1 until we run out of bounds again. So I will have separate positive and negative handling. Anyway, we're gonna run through all of the possible numbers where the answer is in bounds. So let's say I will have another variable, I will call it in bounds. And that is true by default. And while we are in bounds, now we're gonna do that at the very end. The antinode is gonna be the first one. I like the first one better. And add the delta times the multiplier. Exactly. If we are in bounds, that means we have an antinode. We're gonna add that. Otherwise, if we're not in bounds, we're not in bounds. And if we're not in bounds, we're gonna break, basically. Otherwise, we're gonna increase our multiplier by 1. So the next time when it comes along, it will be. Note that for 0, this will definitely be in bounds because we are actually at the first antenna. So we're gonna go up and up and up and up, which makes sense. So now I will redo this exact same code, only in the different direction. We will again set inbound to true, and the multiplier will be -1 this time. This code is exactly the same. This code is exactly the same. This is also exactly the same, but we will now decrease the multiplier. So the multiplier becomes -1, -2, -3, and so on and so forth. So we're going in the opposite direction than this code. It could be done better, but I think I have a feeling that this might work. And once more, we need to return the anti-node location, the size of the anti-node locations. I did a lot of thingies to our original input, so I will copy paste it again. I'm not sure that this is what we actually had. Anyway, let's try it. And we're going for broke. We're saying that we have 34 anti-node locations now, and we were supposed to get 34. So somehow this code works for the small example. Let's see what we get when we run the huge one. Hopefully it will be correct. I think that my logic is logical and that I managed to avoid a few of the holes that we had, namely this thing when we actually find this point as well. But I'm not totally sure. There might be a case that I'm missing. Anyway, this thing says that we have 1067 antinodes now. Let's see if that is actually correct. And that is correct, which means that all of my assumption in this case held. So we have a nice solution that is kind of looking like something. It will be some number, I guess, or something like that. We will see in a couple of days. However, this was quite a mathematical task. We had to do some number analysis, and I don't think that everybody is well versed with the principle of two numbers being coprime and so on. But we got lucky. And to be honest, I'm not that versed as well. If I had to write this code, I could, but it would take me some time, and I would still have to actually test it and put some test cases to see whether this works. I will leave the test cases in, since we want to make sure that this thing actually works. I mean, it provided the correct solution. This solution is very, very fast. It has a lot of nested loops, but those nested loops are kind of constrained because we don't have too many antennas of the same type and things like that. And while these two look like endless loops, they will very fast run out of bounds. So it executes just a few times. Most of this we need to take care that we are not miscounting something. We could use a better set, but for this scenario this is quite okay. And I have to say I might not be too happy with the code. There is a lot of repetition, but I will leave it as is since it solves the problem in very fast time. So that's all for now. If you liked the video, don't forget to mash the buttons, click like, subscribe, whatever you want to do, and keep developing.